for excretion on how to have water and small molecules, both valuable and molecules that are waste or toxins, how do they enter the excretory tubule in these various organisms. And this is the basic idea. There's some kind of filtration. This is for a human or a mammal. The glomerulus for any vertebrate. The capillaries allow water and small molecules carried with it as filtrate into Bowman's capsule here. This is a close-up showing the podocytes wrapped around the capillaries with the water and small molecules coming out between them. Here is a mammalian kidney showing where arterial blood would come in and venous blood leaving. Cortex being this outer region and the medulla being the deeper part in the center. All around the outside is around 300 milliosmoles, the same concentration as arterial blood and venous blood in a mammal. Deep in the medulla here, where the collecting ducts would all be going out in the ureter out to the bladder, it gets as high as 1400. The nephrons start out in the cortex, so they all have their glomerulus in the cortex. This one really should be out here. And they dip down with the loop of Henle, back out to the distal convoluted tubule and collecting duct. How are valuable molecules reabsorbed from the proximal convoluted tubule? Secondary active transport here. Sodium and glucose, sodium and amino acids, and other secondary active transport of valuable molecules. Chloride follows passively because of the charge. And water, if there are aquaporins there, and there are, also follows because as these ions moved out, all the water that was in the hydration shells around the sodium or around amino acid now is free and it moves out. And there would be cells here, of course, and on the opposite side of these cells would be channels for chloride. Sodium-potassium pump keeps moving 3 sodiums out for 2 potassiums in, amino acid transporters and glucose transporters. Things like ammonia, urea, and other wastes, and actually some valuable molecules, can't get them all, get left behind. And because they're in higher concentration, these valuable molecules, including glucose, calcium, and so on, are at higher concentration outside the cell than in the capillary, they will move in through gaps in the capillaries. Here is the descending loop of Henle and the ascending loop of Henle. Why does water leave the descending loop? And why does it matter that salt is being pumped out here? So why does water leave the descending loop? Well, it leaves because of all the salts and chlorides being pumped into the blood supply, the vasa recta, down here, managing about, in a human, about a 200 milliosmol gradient in any one spot, so 500 inside to 700 in the extracellular fluid in the blood. So all this sodium and chloride and actually some other solutes get carried down in, so you wind up with high solute concentration deep in the medulla. As that blood moves past the descending loop, there are aquaporins here, no aquaporins over here, but there are aquaporins here. And so this blood that is in high concentration is meeting fluid that's in lower concentration, and we move more and more water out. So here it's at 300 milliosmol in the beginning of the descending loop of Henle, and by the time we get down here, it would be somewhere around 1200 or even more concentrated. And as we move up here, then we remove the sodium and the chloride, leaving here dilute, very dilute urine, maybe around 60 milliosmoles, but almost all the molecules in there at this point are waste. There's still some sodium and potassium and chloride and calcium to recover, but most of it is waste. If we clamped those blood vessels, so what would happen if we clamped this blood vessel here so that blood couldn't flow? Well, we no longer have the sodium and chloride picked up here, and we no longer have high concentrations here to pick up the water, and so even though the aquaporins are here, water will not leave, and we'll have a lot more water going through the kidney and remaining in the urine. Someone's been drinking large amounts of water. What solute concentrations would you expect at the start of the collecting duct and at the end? So at the start of the collecting duct, we're around 60 milliosmoles. If you've got a lot of water, there's going to be no antidiuretic hormone. So no antidiuretic hormone here. And therefore, aquaporins will not be placed in the membrane. And so the 60 milliosmoles mostly, and the molecules that are mostly waste at the beginning are still 60 milliosmoles and all those wastes at the end. If you do need to concentrate water, then there would be ADH. Aquaporins would get put into the membrane here. Water would be absorbed. And this could get up to as high as 11 or 1200 milliosmoles. But it would have the same amount of wastes. So same amount of wastes here and here. It's just how much additional water remains or is removed.